Hello everybody. Uh, Today we'll discuss about the acoustic log generalities fundamentals. It's all about acoustic log. So uh, this work done by Silhanov Yarasıl, Koyshmanov Salman, Meshtbayev Davletkhan, and me, Omarbek Sabit. So our supervisor, Ablay Nadir. So today we'll discuss about uh, all of them acoustic law. So we'll start about from the overview and after geophysical applications, newer well imagined and acoustical theory and wave propagations. In this theory and wave propagations consists of three waves. And these three waves is compressional, shear and Borehole flexural waves and Stoneleigh waves. So for the first acoustic logging, it's petroleum applications of acoustic wave logging. There are propagation theory in physics, including both surface geophysical method and borehole geophysical method. Acoustic logging is a subset of borehole geophysical acoustic techniques. And historically, the primary and the most routine uses of acoustic log is reservoir engineering have been porosity determination, identification of gas-bearing intervals, and cement evaluation. So about the overview. Today we will discuss about the virtual explosion. And virtual explosion in the volume of acoustic research conducted over the past 20 years has resulted in significant advances in the fundamental understanding of downhole acoustic measurement. These advances in turn have greatly influenced practical logging technology by allowing logging tool design to be optimized for specific applications. Acoustic wave data acquisition method cover a broad range of scales from millimeters to hundreds of meters. So in this diagram you can see there are from millimeter to the hundred of meters. This table 1 lists other common surface and borehole geophysical methods. In this diagram showing the maximum and minimum ranges and versus the resolution for various acoustic methods. Acoustic logging includes the sonic and ultrasonic range. So it starts from ultrasonic and goes by sonic, after that single well imaging, 3D seismic, and finished by 2D. Next table. In this table you can see that the geophysical acoustic reservoir evaluation methods. So acquisition modes, there are surface, reflection seismic, borehole, wireline LWD, and permanent sensors. And for these modes we have geophysical methods. And what geophysical methods we use for these modes. And these modes you can see in this graph. So borehole acoustic logging measurement we'll discuss about after that. In this, modern logging tool includes conventional borehole compensated PHC monopole devices, as well as the newer era devices smooth monopole and multipole, and logging while drilling. LWD acoustic services. Next. In this table, you can see the applications of borehole acoustic data to specific displays. Borehole acoustic logging measurements are used in a wide variety of geophysical, geological, and engineering applications and play an important role in the following undertakings. This table 2 show us evaluation reservoirs, reduction, exploration, and production risk, selecting well locations, designing applications, increasing hydrocarbon recovery. And And the next one, now we'll talk about geophysical application. The high operating frequency of acoustic logging tools and the smaller tier distances allow for the higher quality velocity data and finer vertical resolution than surface reflection techniques. And acoustic log intervals, there are travel time on transit time. Its delta t can be summed and integrated over the entire logged interval to provide the equivalent of seismic one-way time, which compared to borehole seismic surveys and reflection seismic two-way time. And acoustic log data are commonly calibrated using check shot, its velocity, and vertical seismic profile (VSP) surveys prior to using geophysical applications. Data from this survey, which use downhole reservoir and surface acoustic sources, are used to adjust the log data for drift and borehole conditions and result in improved time depth colorations. So the disagreement commonly result from the difference scale and acquisition physics used in seismic and well log measurements. For example, operating frequency, its wavelengths, borehole conditions, angle of measurement, it particularly in the presence of anisotropy. And after this goes near well imaging. Near well imaging that are used in acoustic data acquired that are using with a modern that provide high resolution 0.5 meters and microscale seismic 2D and 3D image structural features in the near borehole region from the 10 to the 15 meters. So there are after this we can say that conventional seismic processing techniques, including filtering and migration, are used to extract compressional and shear reflection from the acoustic data. So the reflections are then used to image geological features near the borehole, and these techniques allow the imaging. There are bed boundaries, seambed strengths, fractures, faults in upper hole and cased wells. There are all of them. These techniques allowed by the imaging second figure. Now this is the second figure, and in these figures there are about near well acoustic image of fluctuated using direct compressional right panel and shear left panel acoustic modems. The next one is acoustic theory and wave propagation. And about acoustic theory. The principles of borehole acoustic logging are based on the theory of wave propagation in an elastic medium as detailed in several results. How I say above, it consists three waves, and one of them is wave propagation. The next, in this wave theory predicts how an acoustic signal propagates through the borehole, and formation Snell's law explains how the acoustic signal behaves at the velocity boundary separating the borehole and the formation. That is, how it's transmitted into the formation and back to the receivers. Elasticity is a property of matter that causes it to resist deformation in volume or shape. It's the elastic nature of rock formation that permits wave propagations. Acoustic waves have four measurable properties. These are velocity, amplitude attenuation, and frequency. So, acoustic wave velocity is controlled by a number of factors. There are lithology, cementation, clay content, texture, porosity, pore fluid composition and saturation, overburden and pore fluid pressure and temperature. So next is about the acoustic wave have four measurable properties. How I said above, there are velocity, amplitude, attenuation, frequency. And in this figure you can see the for borehole logging the models of primary interest are in order of arrival: compressional, shear, Stoney wave. These three waves of the acoustic logging tools. There are acoustic theory and wave propagations. These three waves. And the wave from recorded at the logging tools receives is a composite signal containing different energy models, each with a different frequency, velocity, and amplitude for borehole logging. The generalizing acoustic waveform showing wave signature of different energy modes. So we will talk about these wave propagations, and now we start from the first wave, is a compressional wave. Compressional waves, waves are longitudinal waves that are transmitted through an elastic formation by compressions or pressure. Practical motion is parallel to the direction of wave propagation. You can see this in the figure. They can travel through the solids, liquids, and gases and other phases wave type. They represent the acoustic first arrival. Of all acoustic wave types, they are most renewable because they are least affected by faults, unconsolidated formations, and borehole fluids. And it was about this figure. I said about this figure. And the next and shear and borehole fluctual waves. Shear and borehole fluctual waves, secondary waves, are transverse waves that are transmitted by a lateral displacement of particles in a rigid elastic formation. Particle motion is perpendicular to the direction of motion. And normally shear waves are the second arrival in an acoustic wave train. In most reservoir rocks, shear waves generally have higher amplitude than the compressional waves, but low velocities by as much from 40 to the 50%. There are two types of borehole shear waves. It's direct and indirect, also known as refracted or induced. Indirect shear waves are induced in the formation through a process known as a mode conversion, in which some of the compressional energy is transferred from the borehole fluid into the rock formation. And the next, last one of these waves is the Stoney waves. Stoney waves, it's a tube waves and with a high amplitude guided waves that are generated by a radial. So it's known as symmetric and flexing of the borehole as the acoustic energy processed from the borehole fluid into the rock formation. They propagate at low frequencies along the fluid rock interface at the borehole wall, and hence they are sensitive to the rock properties adjacent to the borehole well. And Stoney waves are also dispersive, and wave velocity varies with frequency. The amount of dispersion is related to formation rock properties. However, Stoney waves are notable for several special properties. There is no cutoff frequency. Dispersion is very mild. For all frequencies, Stoney wave velocity is less than fluid velocity, and group velocity nearly equals phase velocity over the frequency range. and signal attenuation result from the geometry speed of energy through reflection, stratified absorption by the medium through which the acoustic energy travels. So, thanks for everybody. Today we'll stop from this and we'll talk about the acoustic logging and geophysical applications, near-well imaging, and these theories and waves, which consist three waves: compressional, shear, and Borehole flexural Stoney waves. Thanks for your attention. Goodbye.